So next up we have the vulnchat challenge from Tu17 2017. We go ahead and check out the binary, and we see that it is a 32-bit binary right there. We go ahead and check the binary mitigations on this, and we see that NX is the only one that it has. There's no pi, stack canary, or railrow. We go ahead and run the binary. We see that it prints out some text and prompts us for two separate inputs, which we see right here. And let's go ahead and take a look at the binary engager so you can see exactly what is going on. So looking at the binary engager, let's go to the main function. Okay, in the main function, we see that it's printing out the text that we saw when we ran the binary. In addition to that, we see that it is scanning in input at two separate points with scanf. I'm going to go ahead and rename the destination of those two writes, which are stack buffers. And we also see that, interestingly enough, that the format string to those scanf calls is stored as a variable on the stack. We see right here that the format string is initialized to %30s. Reason why it looks that way is because it's a little endian, it's stored backwards. And let's go ahead and take a look to see exactly what we can do with these writes. So our writes each are 30-byte writes, and we see that username is stored at offset 0x1d, password is stored at offset 0x31, and format string is stored at offset 0x9. Taking a look at the offsets real quick, let's see exactly how far we can write with these. We see that the distance between password and username is 0x14 bytes, which is just 20 bytes. So when we write into password, we have a 10-byte overwrite into username, and we see that we have a similar overflow with username and format string. The issue with this is this really isn't enough data to do a nice clean overflow of the return address. However, what we can do is when we have our first input scanned into username, we can use that to overflow format string, and then we can rewrite the format string. Instead of %30s, we could do %100s or just %s. That way we will have a larger overflow of password, and we can overwrite the saved return address. And what is the saved return address? So when it executes a function, I'm just going to pull up one real quick over here. Give me a second. Okay, take for instance this printf call. After this function is done and returns, it needs to know what instruction to execute right after it. That is the saved return address and is stored on the stack. By using the password overflow in order to overwrite that instruction, when the return instruction is executed, we will effectively be able to control what instruction pointer is executed when that instruction right there is executed. So next up, using what I just described, we can probably execute an instruction pointer of our choosing. The question is, what instruction pointer do we want to execute? Looking through the list of functions, we find the print flag function, which will just cat out the contents of flag.txt, so it'll probably give us the flag if we call this function, so we'll be calling this function. We can call this function by executing the instruction that begins the function, which is right here. So if we call this instruction pointer, we will solve the challenge. We'll also need to create a flag.txt file so we can run it locally, but also another way we can find this function is looking through the list of important functions that we see that system is called, and by tracing to see exactly where system is called at, it will also lead us to this function, which we see it right here. So now let's next up see these overflows in action in GDB. I'll be breaking out those two scanf calls, so let's load the binary into GDB. We see the first address is right there. I'm going to set a breakpoint for it. And I'm going to set the next breakpoint right here. Okay, let's go ahead and run it. We have hit the first breakpoint. I'm going to be making the payload briefly for this right now. I want the payload to overwrite that %30s on the stack with %s. We see that the two stack variables just so happen to be the two arguments, so I can just subtract the two to find the offset, which is 0x14 or 20. We also can see the offset here in Ghidra subtracting those two offsets. So it's going to be 20 bytes between the start of my input and the value I want to overwrite. So I'm going to put those filler bytes in there, and then followed by the value I want to overwrite it with. And I'm just going to put in that value right there to execute the first overflow. But before I do that, I'm actually going to see the value stored in memory. Sort of a before and after overflow. Go ahead and execute the overflow now. And we see that we were able to overwrite that value with %s. And then we see when we hit the second scanf, the argument is now %s. We can overflow it with as much data as we want. We see that the offset is 0x31 bytes between the start of our new input and the saved stack return address. I want to overwrite the saved stack return address with just 4 ASCII ones. It will be 0x31, 31, 31, 31. We see the saved stack return address right there. After this overflow, it should be just 4 ASCII ones. And we see right there the saved stack return address is now 0x31, 31, 31, 31. And we go ahead and continue it. You see it crashes because when it tries to execute that saved return address, it is not a valid mapped memory address, so it just crashes. Okay, next up, let's actually take a look at the exploit that we wrote for this challenge. You start off by seeing that we import pwn tools, establish the target process. I attach GDB and break right at the second scanf call. That way I can see the actual overflow taking place. Next up, I receive some of the output from the binary. I do this because it helps with I/O because weird bugs can appear with that stuff. Then I form the first payload 0x14 bytes between the start of my first input and the value I want to overwrite, in this case being the %30s. I overwrite it with %99s. Then I go ahead and send the first payload to execute the first overflow. Then I receive some more output that I'm expecting from the binary to ensure proper I/O. Then I go ahead and form the second payload 0x31 bytes between the start of my second input and the saved stack return address, and then the address of the print flag function, send the payload, then drop to interactive shell. I'll go ahead and run the exploit. I have braked right at the second scanf call. You see that the argument is %99s. I go ahead and look and see that that is the proper saved return address stored at that address. I go ahead and run the scanf call to execute the overflow. I see that I got overwritten with that address right there. And when I go ahead and break at the print flag function, I see that it gets hit. And then I see that system gets called with cat flag.txt. And we see that we get the flag. And then I go ahead and just comment out the gdb.attach and run the exploit without GDB just to verify that we can still solve the challenge. And we see we got the flag, and just like that, we solved the challenge.